Hello? All right, hey everyone, my name is Josh, and I run Moonlight here at 42. If you haven't been to Moonlight before, what we are is we're a side project club here at 42. So what that means is whether you're working part-time or full-time on a side project, it can be a game, an open source project, a company, whatever that is. Moonlight is a place we meet every Wednesday night at 7 p.m. to talk about our side projects. So this week, our demo is Project Live, which we're really excited about. Phil, Eric, and Louie have been working on this project for about 2 months, full-time, right, and like 4 or 5 months part-time. And I've been seeing them in Rabbit Cloud every day, and they've done an amazing job with it. And so they kind of explain a little bit of the differences between, or what, path tracing is, how it can help you with your 42 curriculum, and it should be a really cool talk. So we'll go ahead and get started.
Thanks, Josh. Eric's not feeling too well, so he's going to be sitting this one out, but me and Louie are gonna handle it. Just the quick lowdown on Clive. Yeah, we're as Josh said, we're a Rabbit Cloud project focused on advanced graphics stuff, trying to make photorealistic images. We've got one image here that we're real proud of. We're not going to talk too much about the nitty-gritty of Clive in particular. This presentation is mostly going to be about what is path tracing, how does this whole technology work in a broad sense. Going to try to gloss over some of the hardcore math and just give intuition and sort of base understanding of what's going on. So you want to start us off?
Yeah, sure. So have any of you guys tried out the graphics branch, or specifically RTV1? Yeah, one. Eric, yeah. Okay, well that's nobody. All right, well that's good. We're starting from ground one. Okay, well the basic concept behind the problem that we're trying to solve with path tracing. It's a little abstract, but at the very end of the day, what we're making is a render, and we want to create images. And we want to make images that are better than all the other images that are created by different rendering algorithms. So path tracing is kind of created with the idea of making the most accurate images possible physically. So if you just look here, these two images are obviously different in some way, and there's a few subtle effects that you can kind of intuitively notice between the two, but they aren't immediately apparent. If you were to see this image on this side in isolation, it would look pretty real. I mean, it's shaded correctly. Parts of that should be darker, like under the arm, are dark. Parts that are brighter, like up at the top, are bright. That's what you would expect. But there are certain aspects that get lost in translation, like specifically the way the light bounds off of the sand and bounces up and hits the back of the model and kind of colors it in the color of the sand itself. This is called global illumination. So everything in the environment is actually dependent on not only the light source, but the light source indirectly, and the way the light source bounds off of other objects in the scene and kind of illuminates things that way. So yeah, that's the main aspect, main problem we're trying. So this image, once again, in isolation. This is a standard kind of a ray trace of a scene, a very simple scene in a box with a cube here and a sphere here and a light source that's illuminating the scene. So just like you would expect, it looks very realistic. The light source is illuminating light on the top of the sphere, causing it to be brighter, and parts that diverge away from the sphere are darker and darker and darker, and you can even see shadows cast on the bottom. A red wall is red, a green wall is green. That makes a lot of sense, but there's certain things missing there, and you might not notice until you see what it really should look like, which is this. So that's the difference. This is the problem that we're trying to solve. You don't notice it until it's there. It's something that you're not immersed by this. It looks three-dimensional, but it doesn't look real. And that is a product of all of these secondary illuminations. So if I was to point out a few features, specifically if you look at the sphere on the right side, there's a little bit of red illumination from the red wall here. That's indirect lighting from the light hitting the red wall and then hitting the sphere and then hitting your eye, as opposed to just the white light hitting the sphere. That doesn't get translated in a standard ray tracer. You lose all of that. You don't see any of that global illumination there. On the side of the sphere, you see a green plane here. It's not a green plane sphere, it's a gray sphere, but it's illuminated by the green wall. So yeah, case in point. if you were to express global illumination as a mathematical problem, it looks very intimidating. It's a long integral, lots of variables, you know, who knows really what any of those mean. But we can do.
Not getting into the full depth of it, but just to translate these terms quickly. So what we're saying here is that the light coming out of a point in a particular direction is the light being emitted by that point, like if it's glowing. If that point, this omega here is direction. And then added to that is, this is all of the light coming at that point from every possible direction, and then that's this, and this is the portion of that incoming light that gets reflected in this direction. It's actually, when you don't get thrown off by all the symbols, it's pretty obvious, right? Like that's all the light that there could be, is the light that's coming out. It's a product of the light that's coming in and certain properties of the material that affect how much of it comes out.
Yeah, exactly. This equation basically represents the light from every incoming angle and how that can come out in every outgoing angle, basically.
Yeah, and this little big omega here is all of the possible paths of all of these connections. So we're integrating. Quick show of hands before we move too fast. The word integral means nothing, means a little bit. You know what we're talking about? Okay, cool. Broadly, you know, the most familiar example of an integral is finding the area under a curve, but more broadly, it's the accumulation of lots of tiny contributions over a range. That's, I think, a pretty reasonable way to summarize it. So this is called the rendering equation. It was actually derived in the 80s, but it's very, very hard to compute, so it didn't really see much use for quite some time. Most importantly, it's impossible to solve analytically. By analytically, I mean, like you might remember from high school or college calculus, like the integral of x is 1/2 x squared. Like that's a symbolic actual, like that's literally the answer. This, you can't do that, mainly because it's infinitely recursive. Like this light coming in partly depends on this light coming out. And it's all of the points depend on all the other points. So it's completely, if you try to recurse down this, it just gets bigger and bigger and bigger. All the points all depend on all the other points. So it's kind of crazy. And there's also, it's not explicit in this expression of it, but there's also a term called the visibility term, which is like literally, can light go from this point to the other point? And there's no easy way to talk about that in calculus or really in math generally. So it's a tricky one, but it is the answer to the problem. It's what we're trying to solve. And well, like, you know, we're sitting there wondering, like, if only there was some way to evaluate an integral that you can't actually analytically solve, but there is. It's called Monte Carlo integration. This is a technique that was developed in the 40s, actually on the Manhattan Project. They were trying to solve some extremely complicated math related to radioactive decay and stuff like that. Basically, we're gonna have a little demo actually of Monte Carlo integration to make it more intuitive, but the broad, like the case where you use it, if integration is difficult or impossible, but just evaluating the function at a particular point isn't particularly hard. So like in this case, it is definitely possible to figure out how much light is going along one particular direction. How to figure out how all the light is moving along all the directions is impossible, but any particular point you can evaluate. And we use some cool randomness and statistical methods to use those micro measurements to get a macro measurement. And one of the things that we like to emphasize is this shifts the problem from solving to measuring. We're no longer, ray tracing arrives at a specific answer, and it is some % right, and it kind of can't go past that much. Monte Carlo integration, and particularly a path tracing renderer, actually the longer you let it run, the more correct it gets, and if you were able to let it run infinitely, it would reach the actual literal solution. Despite the fact that it is in some sense kind of impossible to arrive at that answer, it approximates it more and more finely and gets right there. So I'm going to show you how it's pretty intuitive for simple problems. It's harder to apply to more complicated things like rendering. We've had a lot of help from various academic resources, but a quick little demo might show how it works. So let's hop over to this thing that I whipped up today. By the way, if you've never used Google Colab, it's awesome. It's like a pre-set up Python environment that you can import whatever you want. You don't have to worry about installing things, and you can do really neat things with it. So I'm going to frame the problem here. Say that I want to know what pi is, but I don't know a good way to calculate that, right? I don't, off the top of my head, know a good way to calculate what pi is. But I know that pi is in the area of a circle, right? Pi r squared. So imagine that I drew actually I'll just get the graph up. This is going to spoil a little bit, but this will make it easier to see what I'm talking about. Come on. There we go. Okay, so what we have here is a 2x2 square with a circle of radius 1 inside it, right? So the area of the square is 4, and the area of the circle is pi. I don't know what pi is, but I know because the radius is 1, the area of the circle is pi. And if I have so difficult integration, right? Don't know how to figure out what pi is, but an easy evaluation is whether or not a point is in the circle or not. So if I, as I'm doing up here, randomly pick a bunch of points in the square, and then down here, count how many of them end up in the circle, we get something that's pretty close to pi. We're dividing by the area of the circle. So what I'm saying is the ratio of points in the circle to points total is going to be pi over 4, because pi over 4 of the area is the circle, and we're picking randomly from the area. So that was for 1,000 picks, and we got 3 decimal places right. If we go to 100,000, this is just going to look like a solid circle. And this is going to say, well, actually it didn't get that much better. There's a lot of variance, but trust me, as this number goes up, the more accurate we get. So is that making sense to people? Okay, so again, broad strokes, we can evaluate little snippets of a function to get an increasingly accurate picture of the total value of the function, no matter how hard it is to actually calculate that total value. Let's see. So, sorry, I skipped ahead one. So what we do for our thing is we randomly explore the space of all possible paths, tracking the probability of the choices that we made. And then we use that probability to calculate a light value for that particular path. Now, there's infinite paths, but using Monte Carlo integration techniques, we can have each of those give us an increasing amount of confidence about the particular color value of a pixel. This is fundamentally different from ray tracing, where you ask it what the color value of a pixel is, and it gives you an answer. I should put an asterisk on that. There are some ray tracing methods that do involve some element of probability, but this is a total probabilistic approach. And over time, the average approaches the actual solution, and despite the fact that we couldn't have possibly calculated that on our own. So here's a quick little timeline of the image converging. This is over as sample count increases. You wanna walk us through a little bit?
Yeah, sure. I mean, obviously my partner here covered that in very, very, very high detail. But this is an example of an image converging from our path tracer one sample at a time. Well, actually not one sample at a time. This specifically is one sample. So this is essentially a snapshot of what our image, I suppose, what our image accumulates per pixel. So one of these one sample looks like this. 2 of these together, averaged together, looks like this. So this is 2 samples per pixel, and you add basically the color of all of these pixels together, and then you divide by the amount of additions you did, which is 2, so you get the average color of the pixels here. This is 4, so this is basically 4 of these plastered onto each other. So I guess the real question is, why, if you keep adding on the same image, does it get more and more clear? And that's kind of where the randomness of the Monte Carlo really comes into the picture. So it's not exactly the same image getting rendered each time. The thing is, every pixel, when we cast array initially, gets randomized slightly in its direction and its trajectory. And when it goes through the scene and hits objects and bounces off those objects, those bounces are also slightly random. So every time one of these pixels gets sampled, it's going to sample a very slightly different part of the scene, basically. So if we were really to focus specifically on one pixel here that happens to be part of the leaf, you can't really break reality down into pixels, right? Pixels are a finite amount of space. So the leaf could be partially in the pixel and partially not in the pixel. So do you want to draw the pixel as the color of the leaf or not the color of the leaf? And that's kind of where the averaging comes into the play. So half the pixels that are sent, or half the rays that are sent through that pixel will miss the leaf, half of the samples will hit the leaf, and they'll get averaged together, and you'll kind of get a nice middle ground where that pixel doesn't represent only one or the other, it represents both. And so that's 1 sample, 2 samples, 4 samples, 8 samples, 16, 32, et cetera, times 2. And we slowly approach well, not slowly, hopefully quickly approach a very beautifully converged image. This is, what, about 6,000 samples per pixel. So yeah, basically every single sample, or every single pixel on this screen, this is 1024 by 1024 pixels. Each pixel gets sampled 6,000 times. And it's an average, so this red curtain is an average of 6,000 casts on that curtain that happen to make it look that specific hue of red. And that's demonstrated over the entire image. And obviously that's a very costly thing, and there's a lot of optimizations that go into making that a decent process. If you really want to try doing this, I mean, path tracing's been around for decades, yeah, since the 80s, and they've been trying to do this for a long time. And when they didn't have good computers, believe me, it took a long time. You want to take over? Okay.
I just wanted to add one thing. What you said about the multiple samples per pixel, the issue of like an object partly occluding a pixel, that's definitely one of the benefits of the sampling, but it's not just that. So that's anti-aliasing, which you might be familiar with from video games. They do that too, because again, pixels are finite and we're trying to represent something continuous, so we need to blur things and smooth out edges. But there's also, so one particular time that the light ray hits, say, this point on the floor, it's going to bounce straight up. And another time it hits it, it's going to go left. Another time it hits it, it's going to go back towards the back of the scene, because that's what really happens, right? Like in the real world, light bouncing off of a wall's not a mirror. Mirrors reflect things the same direction every time. Walls scatter the light. And we'll talk about that on a future slide about exactly how that process works. But it's important. That's where we get this sort of like ambient light. It's unfortunately the color is a little bit washed out on the projector, but you can see like this archway is actually slightly pink because of some portion of the rays that hit this and turn red, then bounce and hit this archway, and so on and so forth. What's on our next slide? Oh, cool. So important sampling. I was a little bit on the fence about whether we were going to include this in the presentation. This is a little bit more technical, but it explains a little bit about how we, you alluded to optimizations and improvements to get better results for fewer samples. Because obviously doing 6,000 samples per pixel is quite costly and takes a while. We rendered that over a couple hours today. So it's a technique to reduce variance and speed up convergence. That's the word that we use for the approaching the correct answer. It's technically a variant of Monte Carlo, but it's so ubiquitous and so useful that it's basically just part of it at this point. So basically what we do is, instead of completely randomly picking directions, we know certain things about the material properties of the thing that we hit, and that certain directions are going to be brighter. Right, like a good example is like something that's a flat, diffuse surface, like say the black paint on this column. I couldn't prove it, but it's a proven thing that the brightness that you see on it is independent of viewing angle, but dependent on the angle of the light to it, right? And it depends on, basically straight on lights it up more, and glancing angles light it up less. I think that's pretty intuitive. So what we do is we shoot the ray in the direction closer to straight up more often, because that's where we're going to get most of the light from. But if you just do that, you've now biased it to be artificially bright. So what you do is then you compensate by dividing by how frequently you go that direction. Basically, the idea is it obviously like that difference of brightness is continuous, but if you made it simpler, like there were a subset of very bright paths and a subset of very dark paths, and that was it. The number of samples you devote to a type of path is going to improve your variance by like absolute percentage as you do it. Like it'll go, I'm making these numbers up, at 20%, then 10%, then 5%, then 1%, right? And that percent is independent of the actual value, but the absolute error is obviously dependent on that value. Basically, you would much rather be 10% off on the part that's 1 versus being 10% off on the part that's 100,000. So we focus on the high value parts to get it faster. This took a little while for me to like believe that it made sense, but an analogy that I came up with was that, so say that you're running a charity fundraiser, right? Like this dinner event, and all your potential donors are there, right? And you need right now, very quickly, to have a guess of how much money total is going to come in because of this event. Now, it's rude to go ask everyone how much money they're going to be giving, but you could ask a few people and probably not seem too rude. So who are you going to ask? If you know that some of the people are very wealthy and likely to donate large amounts of money, you would prefer to ask those people, because knowing better what your rich donors are going to give gives you a better overall snapshot of the total donations than having a very accurate estimate of people who are only going to chip in $5, right? All of it matters, but some of it basically matters more, and we focus our variance reduction on the parts that are potentially the most contributing. You want to trade off on this one?
Oh, okay, sure. Yeah, that was quite the talk. Okay, so what defines what a surface looks like? That's basically the slide we're on now. So up to this point, we've discussed a few things. Monte Carlo is about the averaging process, about sampling multiple times. This is about how the light interacts with the scene itself. So this, specifically the BRDF, is something, it's a term that you kind of have to set for each material. So objects, when they first get defined in a scene, are usually just a set of basically three-dimensional points that are vertices that describe points on the surface, and you connect those points together and you eventually create a shell that is the object. And when you kind of combined hitting that shell with something called a BRDF, you slowly influence the way that that object looks. Oops, sorry. Just wanted to actually give a few examples. So basically, this is the same polygon object under different material settings. Basically, the light being cast at the object is cast the same way, but the way the light is interacting with the object, the way it reflects off, is different, and that is governed by the BRDF. So there's a few kind of effects that the BRDF initially are really good at. I'm not really sure where to start with. Like, yeah, I should start with like diffuse. Yeah, you can take off for now if you want.
Okay. Yeah, let's first let's talk about this image down here. So these are 3 examples of possible BRDFs, and let me explain. I know it's written up here, but just to be clear, it's bidirectional reflectance distribution function, which is a real mouthful, but basically it means the function that you give 2 directions, an incoming and outgoing direction, and it'll tell you how likely that reflection is, or you could think of it as how much of the light goes in that direction. Those are actually when you're shooting tons and tons of rays, you can see that those are actually kind of the same thing. If it could be, well, rays go in and 70%, they split into 2 rays, and 70% of the energy goes this way and 30% goes this way. That's not really any different if you shoot a lot of rays than saying the ray hits here and it has a 70% chance of all of it going this way and a 30% chance of it all going that way. So this is a diffuse surface. That's what I was alluding to when I was pointing at the column over here. Light comes in and has an equal chance of going in any particular direction. This over here on the far right is a mirror. The light always goes out the exact same direction. And this is a glossy surface, which is kind of a hybrid between the two. You see there's some spread, but there's a definite directionality to it. And it's worth clarifying that these are 2-dimensional slices of what is actually a 3-dimensional function. So it takes both the incoming and outgoing direction as an input, which might not be obvious from this graphic here. So this glossy BRDF, really imagine taking that 2-dimensional image and revolving it in 3 dimensions. That's the actual function that we're modeling. Let's see. So the way we interact with the BRDF is the one I was alluding to, which is evaluating it, which is where you give it both directions and it tells you the likelihood. But the other thing you can do with it that's really important, related to the importance sampling I mentioned earlier, is you can ask it. You give it an incoming direction, you ask it for, give me a likely outgoing direction. And sometimes it'll give you an unlikely one, because those are important too. Those do contribute to the image. But more often you want to go to the more likely ones, so it makes it sort of a continuous probability. Yeah, okay. So that was a lot of theory. In practice, path tracing isn't really that different from ray tracing in terms of the literal code flow that you follow. You still need to figure out what object a ray hits. You still need to pick up its color when you hit it. You still need to store that color in an image buffer or whatever. But basically what we do is, well, I'm not going to read this all out. It's written there. But the key difference between path tracing and ray tracing is the randomly picking a bounce direction. So the light is going to move fully through the scene, and ideally, over many, many samples, we actually explore pretty much the entirety of all the possible paths that the light could follow. Oh, and this is also worth noting, is that we actually fire the rays out of the camera and try to find the light source, just because that's more computationally effective. We only care about the rays that are going to get to the camera, so why think about rays that might not hit the camera? So we shoot out of the camera and try to find the light. But the cool thing about all these equations is they work the same in both directions. Reciprocal is the word that they use for it. Yeah, and then we have just a bunch of screenshots of some stuff that we've been working on. So over here, we're showing off various types of metal. These are actually all using the same BRDF, but with different parameters, these are moving from smooth to rough. And we also varied the colors just to make it a little bit spicier, but the main thing going on here is that this is very smooth metal, and this is rougher, which gives it the glossier, sort of broader highlights, whereas here you have very fine highlights. You can actually see the reflection of the gold car in the chrome car here. Over here is Lucy. She's a laser scanned reproduction of a sculpture of an angel. It's 28 million polygons. And we like to mess around with that because it's just like the highest detail thing that we have. It's how big? It's like 300 or 400 megabytes, I think. You wanna narrate some of these?
Sure, yeah. Not much more to be said, I suppose, but yeah. This is the awesome glass dragon. Specifically, the difference between these two, they have very similar specularities, but obviously the difference is light sources coming from above here, light sources coming from below here, and this is not a transmissive object. So they actually, I think they have the same refractive index technically, but yeah, this just doesn't let light through. So and the next, yeah, and this is one of our proudest renders, just a super high render, high resolution 4K render of the Sponza scene, which is a palace in Croatia, a real palace. And yeah, it's a glossy ass dragon.
This shot is actually a few months old, but we're still just real. We just like
yeah.
75 billion rays gave their lives for this image.
Yeah. And that's about it.
That concludes the slideshow. I hope there will be questions. Are there questions?
So I was just kind of curious, because like NVIDIA and AMD are both, and Intel I think, are all talking now about, I mean they've been talking about it, but now there's new talk emerging of like live ray tracing.
Mm-hmm.
And like, what would be the difference if this was able to be done live versus like their ray tracing?
That's a great question. Yeah, sorry, the mic wouldn't have picked that up. So the question was, recently real-time ray tracing has become something that's being talked about as being right around the corner. And so what would real-time path tracing look like, and would it be better or different from real-time ray tracing? The answer is yes, but so basically, one of the things that's a little bit tricky when you're talking about this distinction is that the barrier between ray tracing and path tracing is a little bit murky. Different authors, different schools of thought about it. Some people would tell you that path tracing is a subset of ray tracing. Some people would say that it's the next generation after ray tracing. It gets a little bit blurry. Basically, let's actually back up to traditional video game graphics, which are raster graphics. In that, if you want to model a particular effect that light has, you have to put explicit code in to model that particular effect. And one of the gorgeous things about path tracing is that you don't. Like for example, we have, like ambient occlusion is something that people like to talk about in graphics engines a lot, the sort of little self-shadowing that objects have. We have tons of ambient occlusion in our images, but we don't do anything to specifically do it. Those parts are just darker because light doesn't get there as often. Ray tracing is kind of in the middle there. Ray tracing can get a lot of those effects sort of, we say like for free or like emergently. They just kind of happen as a natural course of acting. And ray tracing can get some of those, but path tracing, you're going to get all of everything. So for a more concrete example, caustics are a really good example. Caustics are, when you have like a glass of water and the sun is shining through the window and you get those really cool little sparkles on the, That's really hard. It's basically impossible, and well, again, it's not impossible in raster, you just have to write explicit code to approximate it. It's very difficult to get in ray tracing, and it just happens naturally in path tracing. The thing about path tracing is that it's a top-down approach of let's do it as correctly as possible and then try to speed it up, whereas other graphics technology is let's get it to the speed we need to get it and then cram as much visual impact in as we can. So there are some people who are actually working on real-time path tracing. There's this team in New Zealand called Brigade that have been working on it for a little while. There's some really cool YouTube videos out there. I mean, it's still choppy. The images are really noisy, but like, it is gorgeous. Actually, I'm glad I thought of this because I feel like that was kind of a weak answer. The best way to explain, one of the issues with ray tracing is that it is dependent on how many lights there are in the scene, because at every bounce, even though the rays are moving around like they do in path tracing, but at every bounce they're looking straight to the light to see if they can see it. Like they call them shadow rays, and it accelerates the convergence of the image. But if you have lots of light sources, that becomes difficult. Like if you have 1,000 light sources, you're making it 1,000 times slower, naively at least. Path tracing, because the rays don't know about the lights, counterintuitively, it makes it independent of how many lights there are. They just care, when they hit something, they ask it if it's a light, and then react appropriately. We like to talk about the paradigm of ray tracing is fewer smart rays, path tracing is more dumb rays, but you actually end up with a prettier result at the end. Yes?
I get that this is something that's used like a lot in video games, but is there also any way that this sort of thing could be used for like medical applications, like putting up X-rays or stuff like that?
That's a really interesting question. Yes. So the question was whether this has any application to like medical imaging and other fields like that.
Yeah. Specifically, this is based around simulation, and the input data is more around a 3D model. For specifically what you're talking about, I'm specifically about like X-ray images. It's not necessarily an image processing kind of a thing, so it wouldn't you wouldn't be able to input an image per se and then get something out of it through a path tracer. It's more about like giving it an environment and then simulating light in that aspect. But okay, yeah.
It does possibly, though, have real applications in training for things like that that involve visual recognition. Up until now, one of the very few applications of real-time ray tracing and path tracing has been in military simulators for fighter pilots, because they don't just need, like, they can't learn from a video game flight sim because it doesn't look like the real world. They devote tons and tons of hardware to having something where like the glare of the sun off of a building is going to be very realistic and stuff, because you need to be not just training like on principle, but on raw muscle memory and neural just feedback and all that. So if you wanted to generate like very realistic images of, I don't know, some sort of laparoscopic surgery or something like that, and you had the right 3D models, you could. Although I don't know if it would ever be more valuable than just using real world footage of the thing happening. But it's still, it's a very interesting idea, definitely. Yo.
What would happen if you took like an older 3D animated movie from like DreamWorks or Pixar and you used your method on it? What would that do? Could you do that when you get it, powerful enough?
That's a really interesting idea. The question was, what if you applied this technology to an older 3D animated movie or other older graphics thing? So that's really interesting. It would make them look better, basically. I mean, Pixar used to use ray tracing, and now they use path tracing. There's a reason for that. I'm kind of
awesome.
yeah. It would be sweet. I actually don't really have a much better answer than that. The problem obviously is that we would need all of the geometry data, all of the texture data, all of the stuff from them. We can't take the output movie and make better images. But if we had the files that they worked from, we could conceivably make something that looked more natural or whatever. Although I mean, we actually read a lot of stuff from Pixar and Disney in trying to develop this, because they're at the forefront of research on this, and they publish a lot of really cool stuff, and they're not quite as stuffy as like people from Stanford or whatever. They talk about it because they're people actually doing it and working with it every day rather than developing the concepts behind it. So they have maybe some more insight sometimes. And a lot of stuff that they devote effort to is actually artistic control. because while we've been emphasizing how this is super physically rigorous, and it is, sometimes that's not what you want, right? If you want something to look whimsical and cartoonish, you actually want more real art control over what's going on. So we don't necessarily have the infrastructure for that because we've stuck to just physically rigorous exact. They have lots of stuff where they can make put sort of invisible objects in the scene that affect the light in a not physically realistic way to make it look a particular way. Like, if someone's in a spotlight and you really want them to glow more than they would in real life. They have all sorts of procedures for that kind of thing. So we don't have that and maybe wouldn't be able to do it, but now I really want to get some 3D models from some old movies. Yo.
So I have a question. As someone who is did terrible at math in high school and still not very good, and keep in mind that it'd probably take me twice as long to learn this as somebody else, is it practical to still try to learn something like this?
So I think the short answer is yes, you totally could. But the thing is, one of the things that we like to emphasize when we're talking about, because one of the things that Clive is doing is we're going to be making some sort of, we're kind of grinding through the inaccessible research papers and stuff like that, and we're trying to leave behind us a trail of more intuitive, accessible stuff. And the thing is that the math required to prove that this works is insane, but the math required to just do it isn't really that bad. But the thing is, if you ever have a bug, then you kind of do need the more, so it's all a question of motivation. If you struggle with math, but you're really driven to make something like this, I think it's totally doable. But I would warn you that there's definitely math ahead, and you definitely need to be ready for that frustration if you think it will be frustrating.
I also would suggest, I don't think that it's really something you would truck through avoiding the math. It's something that you would probably want to develop somewhat the foundations of, at least linear algebra, and then tackle it would be the, yeah. 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 No, I think it's definitely a doable task. Yeah. Without a doubt.
At the end of the day, most of what we're actually calculating in the program is geometry and some statistical stuff, pretty simple statistical stuff. What's involved in proving that it works is really complicated calculus, really complicated probability, all kinds of stuff that honestly, there's this one paper that's kind of the Bible for this project. It's the thesis by this guy, Eric Veach. He actually won an Oscar for his PhD thesis, which is weird. But it's 400 pages, and it is some of the most dense stuff I've ever seen. And we basically skimmed it to get an intuition, tried to make something like it, and refer back to it anytime our stuff is broken, but we don't work directly from it because we've joked about this. Every time I open up Veach, I start questioning whether anything in our program is right. Yeah. Yeah, so.
Yeah, it's also just largely code agnostic and very theoretical, and so it's hard to apply to something directly that's so hard coded into C and already, yeah.
Yeah, we get more practical help from Stack Exchange.
Yeah.
Anybody else?
What would it take for you, I don't know if you already answered Dylan's question, what would it take for you, either technology-wise or something, to be able to move through this like a game, or to have a whole world where it's not a single image, but like a video game level or a VR level or something?
That's a great question. So being able to do that is just recently being achieved. There's I'll post it on Slack after. There's this wonderful, incredible video that just came out from Lucasfilm and NVIDIA, where they rendered this scene of these stormtroopers in an elevator, and it looks photorealistic, and it's ray traced, and it's real time. But they are doing it on a giant server that costs about $100,000 using brand new GPUs, and not to take anything away from what they did, but they are taking some shortcuts. They have some pre-computed stuff that we don't pre-compute and things like that. But the cool thing is those new GPUs, they actually have literal parts of the chip are devoted to accelerating the difficult work that is required for this. Kind of unintuitively, GPUs are not that good at this. We use the GPU because it's a big brute force calculator that can do a lot of math real fast, but GPUs are not actually very good at ray tracing because they're good at super predictable stuff. basically, if you give a GPU a giant array and tell it, do this function, this predictable, simple function on every element, they're amazing at that. But ray tracing doesn't work that way because all the light is going in all these different directions, it's hitting all these different objects. A big part of the pipeline is traversing a tree, which obviously involves going, the point of traversing a tree is to branch off left and right and start doing different things, right? And so the GPU is not so great at that. But I don't know, do you have any thoughts on that?
I suppose we could mention like filtering. I mean, specifically with path tracing, this image is like a very high sample count, and obviously we wouldn't attempt to render a scene in real time at 6,000 samples per pixel. And one sample per pixel, I mean, quite frankly, looks like butt. But if there's certain mechanisms you can use, specifically filters, that kind of over time, they accumulate data frame by frame, so it's not like you're only analyzing one sample at a time, but you're analyzing this sample plus the last 5 frames or so, and you kind of accumulate those, and it's a way of, there's a lot of different ways of making more out of less, yeah, in terms of path tracing. Ray tracing is already kind of there. Path tracing isn't quite there yet, but yeah, there's definitely mechanisms to make it happen. Big thing is, yeah, just better computers, though. That's the main thing that we need. Yeah. Any other questions?
So for your implementation of path tracing, are you using any of the other like enhancements in its calculations, like using branch path tracing or bidirectional, or are you just going straight path tracing?
Yeah, right now we are using unidirectional path tracing, and we're,
Definitely repeat the question.
yeah. Oh, okay. The question, yeah. The question was, right now in our implementation of our path tracer, are we looking into things like bidirectional path tracing or other optimizations? And the answer is, yeah. Right now, actually, in our development, we're looking into bidirectional path tracing, and we're trying very hard to look through Vicha's thesis of this and kind of parse the very difficult chapter 10 that
But yeah,
revolves.
to be clear, currently all of these screenshots, these are all forward unidirectional path tracing, just sort of the straight vanilla with importance sampling, but that's kind of assumed to be part of it. But yeah, we've definitely been exploring. Bidirectional was, I think we had a kind of a big breakthrough the other day with our theoretical understanding of it. We're going to push forward on it, but for a while it was prohibitively confusing. Basically like the math that you do between bounces and feed forward makes sense, but then you have to, and you do the same thing when you're bidirectional is where rays come out of the light source as well, and then you attempt to join those two paths, and you have to do some extra calculations when you do that joining that are a little bit confusing, but we think it sort of finally clicked the other day. We had sort of a eureka moment at the whiteboard, so hopefully that'll be doable, and hopefully we'll have that pretty soon. And actually that goes back to the question earlier that Andy asked. Bidirectional path tracing is way faster if you do it right. And the really cool, so you've got these rays coming out of normally we're shooting rays out of the camera trying to find the light. Bidirectional, it comes out of the light and out of the camera, and they try to join. And the really cool thing is if you are moving through the scene, the camera has moved, so you need to do all the camera rays again, but there's no reason you can't keep all of those light rays that you shot. So now you have sort of half your work done for you on the subsequent frame. And you can even do things of like pruning them so that the low quality light paths that you made that you're never joining with, you can get rid of those and replace them with better ones. And eventually it accelerates the process quite a bit. We actually saw this intimidatingly impressive WebGL bidirectional path tracer that was like 40 frames per second, a very simple scene in a very small render window, but like lightning fast in WebGL. So if we can get that algorithm working, things are gonna speed up a lot. Yo.
Is there any like AI implementations to
Yeah,
Oh, yes.
absolutely.
Oh, yes.
We should have mentioned that actually in an earlier answer. The question is, does AI have any applications to this field? Yeah, NVIDIA has had startling progress on using neural networks to clean up the sample noise. Several years ago, they did a thing where basically they showed it images with like 100-ish samples and then the converged 100,000 sample images, and it learned how to jump from 100 to 100,000 effectively. Now they've had this even crazier breakthrough where they show it a series of single sample images moving through a scene. It has to have, it can't do it it can't do it as they come. It has to have the whole series to start with. But single sample images moving through a scene, and it can take a neural network can take that and stitch it into perfectly converged images of that movement through the scene. We would love to do that, but we have spent all this time becoming graphics experts, and we're not much on the neural yet. But we'll see. We'll see. All right. Well, I think we'll wrap it up there. Thanks, guys.